Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking find the minimum product of sum defined using NOR gates only. Here we have the function provided in terms of max term. We know that this is a max term by looking at this phi and this capital M. And max term is basically they are talking about the zero, the position of 0. Now let's look at the truth table. If you look at the truth table, you will know what is this represents. So here we have three variables. So A, B, C. Three variables mean 2 power 3. We are going to have 8 different orientations. It's going to go like this. We are going to have 0, 1, 0, 1, 0, 1, 0, 1, and then 0, 0, 1, 1, 0, 0, 1, 1, and the last one is going to be 0, 0, 0, 0, 1, 1, 1, 1. Okay, this is going to be the orientation, right? Now we have to look at the position where we are going to get 0. That's what this max term is presenting. So when you look at the position, it's starting from 0. It starts from 0, 1, 2, 3, 4, 5, 6, 7. And when the max term is given, it means these are the position where we have zeros. So at position 2 we have a 0. So it means here we have a 0. And at position 3 we have a 0. This is a 0. And position 5 we have a 0. And position 7 we have a 0. Others are going to be just 1. So others we can just place 1 right here. Okay. Now here the question is asking to find the minimum product of sum defined using NOR gates only. Okay. Now in order to do this one, first we have to create the function. So whenever they say product of sum, we have to look at the position zeros, and then we have to create the equation based on that. If they ask for sum of products, we have to look at the ones position, and then we have to create the equation based on that. Since they are asking for the product of sum, we have to create the equation based on the position of zeros. Now let's go ahead and do that. This is going to be f of a, b, c. Now if you look at the position of zeros, we have 0, 1, 0, right? In that position, like first 0 is at 0, 1, 0. So 0, 1, 0 mean a is already 0. In order to get, we have to see what we have to have in OR gate in order to get a 0. So in OR gate, we have to have all 3 has to be 0 in order to get a 0. So this means this one is already 0. So we can just write it as it is. And then B has to be, B is 1, but we have turned this one into 0. So we put B complement. So if you put a complement, that's going to turn into 0. And C is already 0. So we can just write it as it is. And the next one is A, B, C. So A is already 0, then B we have to complement, and then C we have to complement. So that's going to give us 0. And then here we are going to have A complement plus B plus C complement. And the last one is going to be what? We are going to have all 3 has to be complement in order to get a 0. So A complement plus B complement plus C complement. So that's going to give us 0. Now let's see whether we can simplify this one. Now in order to simplify this one, we can use one of the equation. An equation says x plus y times x plus y bar is equal to x. And if you want to prove this one, it's easy to prove, because in order to prove this one, we just have to FOIL it. If you cross multiply, like if you multiply everything, you will get x times x. In AND gate, if you multiply xx or aa, the final product is going to be whatever the x value is. If x is 1, that's going to be 1. If x is 0, that's going to be 0. So it depends on x. So this is equal to x and this is a. So it means x times x, that's going to be just x. And then x times y bar, that's going to be just xy bar. And then y times x, that's going to be yx. And then y times y bar, that's going to be 0, because y times y bar is going to be 0, because if y is 1, the y bar is going to be 0. If y is 0, y bar is going to be 1. So anyway, if we have a 0 in AND gate, that's going to be 0. So this is 0. And if we take x common, we are going to have 1 plus y bar plus y. Since we have a 1 in an OR gate, in OR gate we just have to have 1, 1 in order to get a 1. So this means if 1 is 1, it means the whole thing is going to be 1. So this is going to be just x. So this is the proof for this one. Okay. Now we are going to use this one. We don't need the proof, but we are going to use this equation to simplify the equation we derived. Okay, now in order to have this one, we have to have x plus y times x plus y bar pattern. For the first one, you can see if we consider this as x, and let's use a different color. If we consider this as x, and if this as y, and this is going to be y bar, then what we are going to get? We are going to get final product as x. So it means we are going to get a plus b bar as our multiplication. After we multiply, this is going to be the result based on this equation. Okay, and for the next one, we have to rearrange this one a little bit in order to get this pattern. Okay, let's put this one in a bracket, and here what I'm going to do is, if I put the c bar here, you will see the pattern a bar plus c bar first plus b, and then multiplied by a bar plus c bar plus b bar. From this one, you can see this is going to be our x, and this is going to be y, and this is going to be x, and this is going to be y bar. So if we multiply these two together, what we are going to get? We are going to get x again, right? So the final product is going to be but a plus b bar times a bar plus c bar. So this is going to be the final result. Now we had to use this one in order to create the circuit. The question is, let's read the question again. The question is asking, find the minimum product of sum designed using NOR gates only. So NOR gates, now we have to create the circuit using NOR gates only. Okay, now let's see how does this circuit is going to look like first. Here we have two product multiplied. That's why we call this one product of sum, right? We multiply the product, and in order to draw this one, we have to put two OR gates. Those two OR gates connected to an AND gate. That's what this is representing. Okay, let's get rid of this. Okay, let's use a different color. Two OR gates connected to an AND gate. Okay, so this is the result. And in OR gate, we have first one is A, and then we have B bar. B bar means we have a NOT gate connected to B, and the second one is A bar C bar. A connected to the NOT gate, and also we have C connected to the NOT gate. Okay, so these two are going right here, and that's going to be the final result. So we have created this one, but the question is saying design using only NOR gates. This is OR gate, this is AND gate. So in order to get the NOR gate, what we can do is, this one is easy to replace. NOT gate, we can replace this one with the input connected to, if you connect input together and connect it to an OR gate, and turn this one into a NOR gate, like this is equivalent to a NOT gate. So we can replace all the NOT gate with this one. So in that way we will get all NOT gate to NOR gate. But for this one, what we can do is, we can put a NOT right here. If we put a NOT, we have to put a NOT right here too, because this NOT and this NOT cancel each other, so it doesn't change anything. Because if we put a NOT right here, we have to put the same thing right here. So in that way, it's going to be equivalent to the circuit we had before. It's not going to change anything. If you put NOT only here, this is going to change. But if you put NOT here and here, it's going to cancel each other, so it won't change anything. So since we are trying to create NOR gates, this is good because we already create these two into a NOR gate, but we have to do something for this one, right? But in order to create the NOR gate for this one, we have to use the De Morgan's theorem. De Morgan's theorem says, when we have like when we have an AND gate with two NOT gate connected to it, that is equivalent to a NOR gate like this. So let's say this is AB, so this is AB, and this is equivalent to this one. The equation says A dot B all bar is equal, actually A bar B bar, A bar dot B bar is equivalent to A plus B whole bar. So that's it. That's the equation we are getting right here. And also we have another De Morgan's equation, but for this circuit we only need this one because we are trying to change everything into NOR gates. Now let's go ahead and draw the circuit that contains only NOR gates. So first I'm gonna redraw this one. So here we're going to have A, and then we have a NOR gate right here, and this NOT gate I'm going to replace this one with a NOR gate. The input are tied together, so these two are tied together, and we have a NOR gate like this. So that is equivalent to a NOT gate. And then here the same thing, we are going to have something like this, and something like this. Okay, and all of them are connected to this one, and according to De Morgan's theorem, this one is equal to this one, so we are going to have something like this. So this is the equivalent for this one. Okay, and we have to replace all the values, A, B, and this is A, C. So this is the answer for this question. We designed the circuit using only NOR gates, and that's how we do that. And I mentioned De Morgan's theorem equation right here. Let's look at the other one. So there's another De Morgan's theorem equation that says okay, let's get rid of this. A dot B whole bar is equal to A bar plus B bar, and the circuit will look like this. We will have a NAND gate that is equivalent to two NOT gate connected to an OR gate, and this is, if this is AB, this is also AB, and it's the same thing. I hope this helps. Thanks for watching.